อาจารย์พิชชี่เขาอะแต่เขาน่าจะรู้อะโทรไปบอกเขาไหม
อ๋อกล้องคุยเรียบร้อยแล้ว
ต้องคุยอะมันไม่ใช่เราคุย
เขา
อะ
อาจารย์โทรมาหากล้องอะค่ะ
ให้กล้องเตรียมเอกสารไม่ให้เซ็นนะให้โรงเรียนเซ็นรับมาจอมรู้แล้วใช่ไหมเดี๋ยวกล้องต้องออกไปแล้ว It's running. So whenever you're ready.
Good. I don't need to hit play or anything like that?
No, no, just
Okay.
start.
Hello everyone, and welcome to the Smart Curve lesson on chemical equations. Let's go ahead and get started here. Here, our chapter objectives today, we're going to learn how to write chemical equations. We're going to learn how to interpret them. That means how to read chemical equations, how to look at an equation and tell what's going on, what's happening here. And number three, we're going to learn how to balance chemical equations. I want to look at this last point, number three, very briefly. Remember what balance means. Balance means that we have the same thing on both sides. Remember from our lesson on thermodynamics, the first law of thermodynamics says that matter and energy cannot be created and cannot be destroyed. Now this rule is very important when it comes to chemical equations, because in every chemical reaction we have to have the same amount of everything. We have to have the same amount of oxygen on both sides of the equation, the same amount of hydrogen, the same amount of carbon. None of these elements can be created or destroyed. All right, with that in mind, let's move on. We're going to learn how to classify them. We are going to learn 5 different types of chemical reactions to predict the products, to write ionic and net ionic equations. All right. Yeah, remember our lesson on the periodic table there when we look at point 6. We learned about covalent bonds and ionic bonds. Well, we are going to learn how to classify chemical reactions by the types of bonds that are formed between the reactants and the products. All right, yeah, those two words that I keep using again and again, reactant and product. Let's take a look at what they mean. In a reaction, substances join together to form new substances. The original substances present are the reactants. The new substances are called the products. You can think about this like if we're going to make a cake. We take eggs, flour, sugar, milk. These would be our reactants, and the cake would be our product. The same principle applies to a chemical reaction. The things that go in are the reactants. The things that come out are the products. All right. The general form of an equation, reactant to product. That's simple enough. Again, notice reactants go in, products come out. And we always write and read chemical equations left to right, just like the English language. So the reactants are going to be on the left and the products are going to be on the right. Okay? Here, this is the basic formula for a chemical reaction. A plus B yields C. That means substance A and substance B react to produce substance C. And we're going to look at several examples of this later in the presentation. Just quickly, a few more of the symbols we're going to use. The plus is to separate reactants and products. You've seen this symbol in your math class. It means addition. It basically means the same thing here in chemistry. S and L, we use these letters to show the state of the reactants or products. We know different states of matter: solid, liquid, and gas. Very, very quickly, to review these words, if we're going to take water as an example, we know that ice is a solid, water is a liquid, and then steam is a gas. So that's the same chemical, the same substance in different states of matter, right? And here, that continues on the next slide, number 8. We have the symbol G, meaning a gas, like when water becomes steam. The AQ means the chemical is dissolved in water. This is actually very common to see in chemical reactions because there are many different chemicals that dissolve in water. Water, if you remember from our lesson on the periodic table, water is the universal solvent. And there's a reference in the book there that you can check out. Let's move on to slide 9. That symbol delta means something is added. The little green triangle, that's the Greek letter delta. In chemistry and physics, delta almost always means change. So in chemistry, it means something is added to the reaction, and usually this means heat. So heat energy added to a reaction. And then the blue arrow means a catalyst is added. Alright, so when we talk about chemical equations, let's first talk about the skeleton equation, the skeleton formula. This is a very rough form. It only shows us the elements themselves, or the reactants and the products themselves. It doesn't tell us anything about the ratio. It doesn't tell us anything about how much. Here's an example. Sodium metal reacts with oxygen gas to form sodium oxide. When we write that in the skeleton, when we write that as a skeleton equation, we don't write anything about how much sodium or how much oxygen are going into that equation, or how much sodium oxide is coming out of that reaction. We just write the names of the chemicals, the elements, and the compounds. All right? Review. Here's you can test yourself on slide 12. Magnesium metal reacting with chlorine to form magnesium chloride. Here on slide 13, the law of conservation of mass. Remember, this is just like our first law of thermodynamics, if you remember our lesson from that unit. Remember, matter and energy cannot be created and cannot be destroyed in a chemical reaction. because of this law, it is necessary to balance. So in any chemical reaction, we have to have the same amount of every element on both sides. We have to have the same amount of sodium in the reactants and the products, the same amount of oxygen in the reactants and the products. Let's take a look at that. Here we go. And this is what we call balancing equations. Remember, again, balance means having the same on both sides. In balanced chemical equations, each side has the same number of atoms of each element. The same in the product, the same in the reactants, and the same in the products. All right? And to do this, we have to use coefficients. These are the large numbers that we put in front of a compound or an element in a reaction to balance the chemical equation. Now we're going to take a look at that. I'm going to give you an example here. But first, let's go through a few questions. What is the difference between a coefficient and a subscript? Well, I'll give you an example. Let's take this. Here's a chemical formula that many of you are familiar with, H2O, the formula for water. Notice our coefficient is written before the formula, and the subscript is actually a part of the formula. Now what this means is that a water molecule has 2 hydrogen atoms and 1 oxygen atom. Like this. Our coefficient means that we have 2 molecules of H2O. Like this. So our subscript is part of the formula. So we would never, ever use subscripts to balance an equation. Say, for instance, I wanted to balance an equation by adding more oxygen. Now, if I were to do that by adding a subscript to make this H2O2, well, this is no longer water. We would be creating a completely new molecule. And we can't do that in chemistry. That's why we never use subscripts to balance the equation. We only use coefficients. All right? Rules for balancing equations here on slide 16. Okay. There we go. Again, determine the correct formulas for the reactants and the products. Again, the reactants are going to be on the left side and the products will be on the right. We read a chemical equation left to right, just like we read written language, just like we would read a sentence in English or in Thai. Here we go. Count the number of atoms of each element present on both sides of the equation. Balance the elements one at a time by placing coefficients in front of the formula, and check to make sure each atom is balanced. We're going to take a look at that, I think, right now. Why don't we... Check to make sure that all coefficients are in the lowest possible ratio. If no coefficient is written, the coefficient is assumed to be 1. All right, let's do an example together. Let's balance that first equation. I'm going to grab a scratch piece of paper. H2 plus O2 yields H2O. There we go. Now, the reason we have this subscript for hydrogen and oxygen is because both of these elements are diatomic in nature. Oxygen is always found bonded to another atom of oxygen. This is an oxygen molecule, a diatomic molecule, and the same is true of hydrogen. Hydrogen is never found by itself. We never find a lonely hydrogen atom. It's always paired to another hydrogen atom. To understand why, remember our lesson on ionic and covalent bonds when we learned about the periodic table. Remember, Hydrogen's atomic number is 1, meaning that it has 1 proton and 1 electron. Remember that first energy level in an atom has room for 2 electrons. So hydrogen has 1 electron in an energy level that has room for 2 electrons. So it has 1 empty space in that valence energy level. So with hydrogen, you've always got one electron, 1 space, 1 electron, 1 space. So 2 hydrogen atoms very naturally pair with one another to fill that valence energy level, that valence shell. And the same really is true of oxygen. Alright, so let's go back to our equation. H2O2, yielding H2O. Notice, in the reactant side, we have 2 atoms of oxygen. However, on our product side, we only have 1 atom of oxygen. Now remember, we cannot use a subscript to balance the equation. We have to use a coefficient. So if we've got 2 oxygen atoms here, and we need to have 2 here, the natural thing to do is add a coefficient of 2. Now we have 2 oxygen atoms in the reactant side and 2 on the product side. We're balanced. But now we've got another problem. Our hydrogen is no longer balanced because we have 2 hydrogen atoms in the reactant side and 4 hydrogen atoms in the product side. 2 times 2. Well, all we have to do is add a coefficient of 2 here. Now, we have 2 molecules of hydrogen plus 1 molecule of oxygen yields 2 molecules of H2O. Our reaction is balanced. We have the same number of atoms of hydrogen and oxygen in the reactant side and the product side. I'd like you to try the other ones on your own, sodium and bromine, along with silver nitrate and copper. Again, here, more examples, iron and oxygen, then aluminum oxide and hydrogen, yielding aluminum and water. Right. A few more. Okay, let's go on there to slide 24. I do want to look at this equation on the very top. Remember, we saw earlier in the slide, earlier in the slideshow, we saw a chemical reaction with, here, sodium hydroxide. Let me find that. Actually. Ah. I apologize, I am getting a little bit ahead of myself. I want to come back to slide 21. Let's look at problem number 1 in the quiz. We have, again, slide 21. In this equation we have FeCl3, iron chloride, plus NaOH, that's sodium hydroxide, yields iron hydroxide and sodium chloride. This is actually a fairly common chemical reaction. Here, our iron chloride, this is like a green or reddish crystal. Sodium hydroxide, a very common chemical, commonly known as lye. It's used to make paper. It's used to make soap. Your chemistry laboratory at school probably has a very large jar of it. It comes as little white pellets. All right. And in this chemical reaction, it's going to react with the iron chloride to make iron hydroxide. Iron hydroxide is used as a pigment. That means it gives color to things. It's used in cosmetics like makeup, and it's also used in tattoo ink. Specifically, it's used to make yellow ink. So if you see somebody with a tattoo that has yellow, it's probably iron hydroxide. I do want to give you an example of how to balance an equation by balancing this one for you. Let's start, remember we go one element at a time, so let's start with the iron. In our reactant side we have 1, in the product side 1. So far so good. Let's move on. Next, chlorine. In the reactant side we have 3 atoms of chlorine. However, on the product side we only have 1, in that sodium chloride molecule. So we have to add a coefficient. For 3 in the reactant side, for 3 on the product side, we have to add 3 into the reactants. We have to add 3 onto the product side. So we have 3 molecules of sodium chloride. Well, now we've got 3 atoms of sodium on the product side, but only 1 on the reactant side. So now we've got to add another coefficient to balance the sodium. There we go. Now we have 3 sodium atoms in the product side and 3 sodium atoms in the reactant side. Now we have 3 hydroxide ions, and notice here we have a subscript of 3 giving us 3 hydroxide ions in the product side. So now with these 2 coefficients, everything's balanced. The iron is balanced, the chlorine is balanced, the sodium is balanced, and the hydroxide, the OH, is balanced as well. I want you to keep this one in mind. The sodium hydroxide, also known as lye. This chemical that's used to make paper and soap and detergent. Remember this because we're going to move on and look at lye in another type of chemical reaction on slide 24. Here we see lead nitrate and sodium hydroxide, or lye, sodium hydroxide, reacting to make lead hydroxide and sodium nitrate. This is a very interesting chemical reaction. We have lead nitrate, which could be used as a fertilizer, and sodium hydroxide, Li, reacting to make sodium nitrate. Sodium nitrate is an explosive. So this chemical reaction tells you how to make, this chemical reaction shows the production of an explosive. Sodium nitrate is used to make bombs. Now, that nitrate, NO3, is found in a lot of different fertilizers because it can be used as plant food. So this shows you how fertilizer and Li are often used to make an explosive. And this is what's often known as a fertilizer bomb. Let's move on. To balance equations, you must remember to write correct chemical formulas, obviously. Slide 26. I do want to look at that second point. Remember that the diatomic elements appear with a subscript of 2 when they are alone. We see a row of letters here. These letters represent the elements that will always be diatomic. Br for bromine, I for iodine, N for sodium, N for nitrogen, Cl for chlorine, H for hydrogen, O for oxygen, F for fluorine. All of these atoms will almost always be diatomic in nature. And we saw 2 of those in our chemical equation for water. Remember, the hydrogen and the oxygen are always going to be diatomic. They're always going to have a subscript of 2. Okie dokie. More examples there on slide 27. On slide 28, we see the different types of chemical reactions. Remember I said at the beginning of the lesson that there are 5 basic types. Here we see them. Synthesis, decomposition, single displacement, double displacement, and combustion. Let's look at each of these types of reactions one at a time. We'll start at the beginning with synthesis. Synthesis reactions are also called combination reactions. A synthesis reaction occurs when 2 substances combine to form a new compound. Our equation like that, think A plus X yields AX. So we have 2 reactants combining to form one product. So AX combined to form AX. Let's look at a few examples. Magnesium and oxygen form magnesium oxide. Iron and chlorine form iron chloride. Uranium and fluorine form uranium hexafluoride. Notice in all of these we have 2 reactants, 1 product. 2 reactants, 1 product. 2 reactants, 1 product. Synthesis. The next, decomposition. This is when we go the other direction. When we have 1 substance, 1 compound, which breaks down into smaller compounds or elements. So 1 substance breaks down into 2 or more simpler substances. And our reaction just goes the other way. AX yields A and X. So, some examples. We see the first one. Mercury oxide breaks down to yield mercury and oxygen. calcium hydroxide breaks down to yield calcium oxide and water. H2SO4, that's sulfuric acid, breaks down to yield SO3 and water. Alright, so a few practice problems for you there. Write a correct balanced equation for the synthesis of KCl, that's potassium chloride. Let's do that together. Synthesis, remember that's A plus X yields AX. So in this case, that's going to be potassium plus chlorine yields potassium chloride. Easy, right? But remember, chlorine is one of our diatomic atoms. Remember back from page 26. That's Cl, chlorine. That's one of our diatomic elements. So chlorine has to have a subscript of 2. Well, now we have 2 chlorine atoms in the reactant side, but only 1 in the product, which means we have to add a coefficient of 2 to the product side. 2 molecules of potassium chloride. Well, now we have 2 molecules of potassium chloride, 2 atoms of potassium, only 1 atom of potassium over here. We have to add another coefficient. Now everything's balanced. 2 atoms of potassium, 2 atoms of chlorine, 2 atoms of each. Alright, here we go. There, and that's the synthesis of potassium chloride. Alright? More problems there for you to do on page 35, 36, and 37. I will let you do those on your own. Again, 38 and 39 as well. Okay, let's move on. The next type of reaction we see on page 40, slide 40, that's a single replacement. In a single replacement reaction, an element reacts with a compound. Now this is like, so A plus BX yields AX plus B. This is like going to a party and you've got maybe a playboy X who comes to the party with one girl, B, but he leaves the party with another girl, A. Or if you prefer, you can do it the other way around. A girl X who comes to the party with one boy and leaves with another boy. All right. Single replacement. Let's look at an example of that on slide 41. We have Mg, magnesium, plus zinc nitrate yields magnesium nitrate plus zinc. So magnesium and zinc are going to be our 2 ladies there, and the nitrate will be like our playboy. The playboy arrives to the party with zinc, but he leaves the party with magnesium, and zinc is all alone. The same thing happens in the next one with magnesium and silver nitrate. The nitrate arrives at the party with silver, and it leaves with magnesium. Not all single replacement reactions occur. You can determine if a reaction will occur by knowing the activity series of metals. See our handout. Okay, now this is interesting. Remember, all of our metals have a different atomic number, and therefore a different number of electrons and therefore the electrons are arranged in a different way. And the way the electrons are arranged in these shells will determine just how reactive an element or a metal is. In our series, notice the more reactive metal will always replace the less reactive metal. Look at that point 3. Any metal that is above another metal in the activity series will replace the less reactive metal. Look at that again. The more reactive metal will replace the less reactive metal. Keeping that in mind, let's go back to slide 41. Notice, in that first reaction, the magnesium replaces the zinc. That means that magnesium is more reactive than zinc. In the second equation, the magnesium replaces the silver, Ag. That means that magnesium is more reactive than silver. Magnesium is a very reactive metal. All right. And our handout does have the activity series of metals. And if you look at that series, you will notice magnesium is above zinc and silver. It is more reactive. That's why it replaces them. All right, let's move on. Whoop. Here we go. Here's our activity series. Notice our most reactive metal is lithium. Notice magnesium is here at number 5, below lithium, potassium, calcium, sodium, magnesium. Notice zinc down here at number 7, and silver way down here at the bottom. So that magnesium, because it is more reactive, is always going to replace zinc or silver. All right, yeah, let's take a look at that. Predict if the following reactions will occur. Bing. So, iron plus H2O. Notice, so our question there is, will the iron replace the hydrogen? Well, let's take a look at our series. Notice the iron is right here. The hydrogen is 2 spots below iron. That means that iron is more reactive than hydrogen. So the answer is yes. Iron will replace hydrogen. We'll get the compound iron oxide, which is rust. Most of you are familiar with this. If you take something that is made of iron and you let it get wet and you let it sit there, it will get rusty. This is because the oxygen is leaving the hydrogen to be with the iron. The iron is replacing the hydrogen because it is higher in the activity series. It is more reactive than hydrogen. Let's move on and look at the next one. We've got magnesium plus lithium nitrate. Well, look, our magnesium, remember the magnesium replaced the zinc and the silver because it is higher in the series. It's more reactive. However, it is below lithium, meaning that lithium is more reactive than magnesium. So magnesium will not replace lithium in this reaction. So will that reaction occur? The answer is no. Let's look at the next one. Number 3, we have sodium and silver chloride. Let's look at the question we have to ask, will the sodium replace the silver? Will the sodium replace the silver? Let's look at our activity series. Notice our sodium is right here, number 4. Our silver is down here at the bottom of the list. That means that sodium is higher in the activity series. It is more reactive than silver. So yes, it will replace silver in that compound. So we'll end up with silver and sodium chloride. You can test yourself there, slide 46, writing balanced equations for those reactions. Predict the products in balance on slide 47. Again, use what we've learned with the activity series and use what we've learned about balancing equations, making sure we have the same amount of each element on both sides. And remember to look at it one element at a time. The next type of reaction, double displacement. In a double displacement reaction, 2 compounds react. The compounds swap elements with each other. This would be like the compounds contain a positive and a negative part. In a double displacement, the positive parts swap places with each other, as do the negative parts. Remember, with positive and negative, we're dealing with ionic bonds. This would be a little bit like a double date, where the partners come to the dance like this, and then they switch partners. To give you an example, we've got lead and lead chloride and lithium sulfate yields lead sulfate and lithium chloride. So the lead, and imagine the lead and the lithium switching. The same thing happens with in the second example. We have zinc bromide and silver nitrate. We end up with zinc nitrate and silver bromide. Predict the products of the following reactions. All right. So we're gonna have another switch there. All right. And finally, the last type of reaction, number 5, combustion. This is where we have a hydrocarbon reacting with oxygen. And the products are going to be carbon dioxide and water. Example of hydrocarbon would be a sugar. So if we burn sugar, for example, that's going to be a combustion reaction, producing carbon dioxide and water. Here we see an example, 2C6H6 plus 15 oxygen atoms yielding 12 molecules of carbon dioxide and 6 molecules of H2O. And as you notice, they commonly require very large coefficients. In this case, we end up with many molecules of diatomic oxygen and many molecules of carbon dioxide. Write the balanced equation for the following combustion reactions. The one I want to look at there is B, C6H12O6. And the reason I want to take a special look at that is because it is such an important molecule, that is glucose. So when we write a combustion reaction for glucose, this is actually how your body gets energy. So here we go. Let's do. Remember what we've learned. We've got our glucose. Remember C6H12O6. Remember what we've learned about a combustion reaction. We're adding oxygen, and our products are always going to be water and carbon dioxide. So let's dive in and try to balance this equation. Notice, glucose, we have, let's start with the carbon. We have 6 carbon atoms in glucose. However, here we only have 1 in the product side. So to balance that, we're going to need a coefficient of 6, and thus create 6 molecules of carbon dioxide. So now we're balanced with respect to carbon. Let's move on to hydrogen. Notice we have 12 atoms of hydrogen and only 2 here in our product side. So we're going to require a coefficient of 6. 6 times 2 is 12. So 6 water molecules will give us 12 hydrogen atoms. So we're now balanced. 12 atoms of hydrogen here in the glucose and 12 atoms of hydrogen here in our 6 water molecules. So now, the final step, let's take a look at the oxygen. Look, we've got 6 atoms here, 2 here, that's a total of 8, 6 here, and 12 here, that's a total of 18. So we have 18 oxygen atoms in the product side and only 8 in the reactant side. The way we can balance this, though, is actually quite simple. We just need another. Look at that, another 6. Now we've got 6 times 2, 12, plus 6, 18, which is just what we have here in the reactant side. So now we've got 18 atoms of oxygen in the product side, 18 in the reactant side, and our equation is balanced. Okie dokie. And that would be the combustion of sugar. Independent practice. Here you can practice that on your own. Predict the products for the following reactions. Remember to use what we've learned. Finally, let's look at ionic equations. Ionic compounds often dissociate when dissolved in water. A good example of that is sodium chloride. We form positive sodium ions and negative chlorine ions. Remember what we learned in our last lesson on the periodic table. Why is that? Why do we have sodium and chlorine ions? That's because, remember our subatomic particles. We've got our protons that have a positive charge and our electrons that have a negative charge. So to have a charge of +1, like the sodium, we have to have 1 more proton than we have electrons. In the case of sodium, that means 11 protons and 10 electrons, giving us an overall charge of +1. The chlorine, remember, has 17 protons and 18 electrons, because that chlorine atom takes an electron from the sodium. So the sodium goes from 11 protons and 11 electrons to 11 protons and 10 electrons, giving it a positive charge. So we write Na+. The chlorine goes from 17 protons and 17 electrons to 17 protons and 18 electrons, meaning it has one more electron, one more negative charge, so we give it an overall -1 charge. All right? Boom. Soluble versus precipitate. Soluble means the compound breaks down into its ions in water. That's like salt. Sodium chloride will break down into positive sodium ions and negative chlorine ions. Sodium chloride is water soluble. Insoluble would mean the compound does not break down in water. Here, we see that, we see on slide 58, we see that in double replacement reactions. Often one of the products will be insoluble, and the insoluble product is referred to as the precipitate. Determine whether each is soluble or insoluble. Our rules there are on the EOC sheet. So use your EOC sheet to do the practice problems on slide 59. Okay, to write a complete ionic equation on slide 60, write the aqueous substance as ions. A good example of that, we have silver nitrate, which is aqueous, plus sodium chloride, also aqueous, yielding silver chloride and sodium nitrate. Again, we know some of these products and reactants and products already. The NaCl we know is table salt, and that sodium nitrate we know as the explosive. Okay. All right, let's move on. All right, more practice writing ionic equations. And one more point to make about these ionic reactions is very often we have what are called spectator ions. Remember what a spectator is. A spectator is someone who is watching something take place. For example, if you go to a football game, you have the two teams competing on the field. The spectators are the people in the audience, the people who are just watching the game. A spectator ion is like a spectator at a sporting event, like a spectator at a football game. They aren't actually playing the game, they're sitting on the side as if they were watching it. They show up on both sides of the equation, they cancel one another out. And the net ionic equations indicates the particles that actually take part in the reaction. It does not include spectator ions. Alright, so net ionic equations. Okie dokie. That about does it for our unit on chemical equations. Again, you want to go through and do those problems on your own. We did demonstrate a few of them, but in order to really learn how to do this, it's best to learn by practicing as many as you can. Just remember the rules that we learned, and I'm sure you'll be able to do it. So, good luck, and I will see you next time. All right?
So I guess you all will be coming in again tomorrow.